QAOA. An approximate solution to the Knapsack problem can be simulated on a quantum computer using a quantum approximate optimization algorithm, or QAOA for short. For a given combinatorial problem, formulated as a function f, which we want to maximize, we design a Hamiltonian, which models our objective function. To apply the QAOA algorithm, this Hamiltonian should be presented in a form of a quantum circuit. The connection that allows describing a quantum circuit in terms of Hamiltonian is established by a time evolution. The time evolution operator is a unitary operator generated by Hamiltonian. Any unitary operator can be written in the form exponent to the power of I gamma h, where gamma is a scalar and h is a Hermitian operator interpreted as a Hamiltonian. This operator can then be decomposed into a sequence of quantum gates, which are physically applied pulses with certain durations. A classical example of a QAOA application is to solve the max cut problem. For that problem, the number of qubits which is required is equal to the number of nodes in the graph, and the task is to find a combination of nodes that fulfill a certain condition. So, first, we apply Hadamard gates to create a uniform superposition state. Then, we let the system evolve alternatively under two parameterized unitary operators generated by two Hamiltonians, h and b. Here, xjth is a Pauli x operator acting on the jth qubit. The unitary operator associated with the Hamiltonian b is called a mixer, and what it is mixing will be shown in the part 4. So, we do it p times to create a trial state. Then, for a fixed p, we need to optimize the set of parameters gamma and beta to maximize this expectation value. Right now you are probably wondering, why do the samples from the final state with an optimized set of gammas and betas give us a state which will, with high probability, maximize the target function? To answer this question, we need to recall the model of adiabatic quantum computation, which is based on a theorem known as the quantum adiabatic theorem. This theorem says that if we take a quantum system whose Hamiltonian slowly changes from h1 to h2, then, under certain conditions on h1 and h2, the ground, the lowest energy state of h1, gets transformed to the ground state of h2. This is used to construct adiabatic algorithms for optimization problems. We take a Hamiltonian h1 with a known ground state, and a Hamiltonian h2 whose ground state corresponds to the solution of our optimization problem. Then, preparing a quantum system in the known ground state and slowly changing the Hamiltonian from h1 to h2, we will solve our optimization problem. A uniform superposition state, which is used as an input state for QAOA, is also the ground state of operator -b and corresponds to the largest eigenvalue of operator b. So, it is the state which maximizes the result after the evolution under Hamiltonian b. And slowly varying gamma and beta, we will go from the state which maximizes b to the state which maximizes our objective function. Therefore, for properly chosen beta and gamma, in the limit of infinite number of steps, the final state of the system tends to the exact solution. There are several ways to optimize the vectors gamma and beta. How to choose p is also a separate question, and it is beyond the scope of this video, and further information you might find in the description.